Okay, my name is Clemens Kolbitsch, and together with my colleague Sylvester Keil, we're going to talk about fuzzing and exploiting wireless device drivers. Just a short outline for today. The first thing we're going to talk about real briefly is 802.11 fundamentals, so how does wireless protocols work. The second thing we're going to talk about is the fuzzing of the wireless protocol itself. There are several issues connected to that, and we're going to talk about how we might overcome these, and that's the third point, actually what we call virtual 802.11 fuzzing. That's our new approach to do the fuzzing itself, and we're also going to have two short demonstration of our new tool. And as a fourth part, as the last part, Sylvester is going to talk about how we could maybe exploit the things we find with fuzzing in kernel mode. Okay, to give a short introduction, of course, first about ourselves. Right now we're two students at the Technical University here in Vienna. We ought to be working on our master's theses, like Engin probably knows, but we have quite a lot else to do. One thing we did is the work that we present here. This is the result of a vulnerability seminar that we did at our Secure System Lab together with SecConsult. For those of you who don't know SecConsult, it's one of the only companies in Austria that do high-tech research in the security area, and they have regular participants at conferences like Black Hat or DeepSec right now. And what might be interesting for you guys is that they have a vulnerability bonus program where they buy new vulnerabilities. So there's one way for you guys out there to make a little money, and there's a URL and also an email address on there, and it will be on the wiki, so you can look it up later if you're interested. So to get back to our real wireless playground, first, all of us know that wireless networks have become a wide standard. Like every one of us has probably some wireless device, either in your laptop, in your standard computer. You also already have them in your phones, you have them on your PDAs, even on your MP3 or video players. That basically means that there's a vastly increasing number of potential targets out there. And what's even better about it is that the communicating software, the device drivers, operate on a very low level supervisor mode, that is kernel mode in Linux talk. So every vulnerability that we find in there turns out to be extremely dangerous and a lot of fun to play with. So we're going to give you a short 802.11 primer. For those of you who know the protocol itself, I know this is really a summary of what's there, but that's all our time gives us. So to see where we're operating, most of you probably know this picture. It's the IEEE 802 family for connecting computers. And we have a lot of standards in there, but the one that we're interested in is on the right, on the blue. That's the 802.11, which is wireless communication. And it's split up into two layers. The first one is the physical layer on the bottom, which is divided into multiple sections where the device treats things like different transmission modes and so on. Everyone has heard of A, B, G, and so on. However, we're not going to deal with that stuff because that's all melted into your hardware, so we don't want to exploit your hardware. I mean, you can go ahead, but we don't want to. What we deal with is the thing above. It's the MAC layer, because that's in software and we can deal with that stuff. Okay, so inside the MAC and inside the wireless protocol altogether, we have three different types of frames. We have management, control, and data frames. The management frames are there for really advertising and connecting to networks, wireless networks. The second thing, control frames are really used for management of who is talking when and so on. However, we don't really go into the control frames because we don't see any potential vulnerabilities in there. And the third type is the so-called data frames, and that's exactly what the name suggests. It's really for transporting higher level protocols over the wireless medium. Down here we have a picture of a management frame, and it's made up just like any protocol usually. So we have a header, we have a frame checksum at the end, and we have a body. We have multiple addresses, I will get to that in just a second, and inside the body we have so-called information elements that carry information about wireless networks, and I will deal with that in a second as well. So here we have what is called the wireless states. We have three different states, which basically divides the types of packets that might be sent over a network. We have state 1 where both devices don't really know anything about it or about each other. We have state 2 where they have little knowledge about each other, and then in state 3 we have full knowledge of both devices and they can transmit higher level protocols. And how all that works can be seen in what's so-called association of two devices. In this example, we have an access point on the left and a station on the right. And I will just show you how this works out, how they can connect to each other. The first thing we have on the left side, on the access point side, we have that the access point is sending out so-called beacon frames. A beacon frame is nothing else than a management frame that contains information like, hello, there's a network available, its SSID, its network name is, I don't know, my network. I'm talking on channel 9 and I support the following rates. So that's all there is about this beacon frame. The second thing that is there is the station's first thing it can do to get a connection is send out a probe request. It's again a management frame of a special type, and it just says, hi, well, I want to know more about your network. So when the access point gets a probe request, it will reply with a probe response, and again including the data that was in the beacon frame, and it might add some additional information. But basically a probe response is nothing else than a beacon frame, but sent out as a reply to a request. So when the station, for instance, my laptop says, hey, I want to connect to that device or to this network, it sends out an authentication frame. The authentication frame is basically, hi, well, my MAC address is something, and here's sequence number 1. And if the access point wants to build up a connection with that station, it just sends back, yeah, hi, there's this my authentication, there's sequence number 2, and this is my MAC address. Although authentication might sound something like security, it really has nothing to do with it. It's really just exchanging MAC addresses and sequence numbers, so they have a starting point to build their connection on. So as soon as this authentication has been done, we're in what we saw before called state 2. This is authenticated but not associated. So the next thing that has to take place is the association itself. Again, it's a request from the station basically saying, well, I know your MAC address, hello, Mr. Access Point, I want to connect to your network. Here's the parameters you might know need for authentication. And if the access point wants to build up the connection, it again replies with an association response welcoming this new station in the network. Right now, after this association, we're in what we saw before, state 3, where we can send higher level protocols that might be UDP, IP, UDP, IP, TCP, IP, and so on. And they might also start doing some encryption, send out key information files, and so on to get real encryption and authentication in the network. So we now know how wireless communication really takes place, and I'm going to talk a little bit about fuzzing and what's the problem with fuzzing wireless protocols. Well, the first thing is that typically fuzzers go ahead, I mean, I think you all know what fuzzing is really sending out tons of probably random data and see just what happens. But there's a huge problem when doing this with wireless devices. There's been some or even a lot of talk at the Black Hat Europe this year about fuzzing wireless device drivers. But they really stated some issues they simply couldn't deal with. One thing was the frequency channel problem. Whenever a laptop sends out a frame, for instance, probe requests, saying, well, are there any networks in the area? It sends out this frame at a particular frequency. And if it doesn't receive anything in a few microseconds, it will change the hardware frequency to some other frequency and then send the packet again. So whenever you send out some fuzz data at frequency channel 1 and laptop is in frequency number 3 because it's constantly iterating through all frequencies, you're just missing tons and tons of data and you don't even know it. So that's a really big problem. Another thing that we have is that there's a lot of hardware filtering going on with the incoming packets concerning the BSSID, the network ID, and also of the states that you saw before, state 1, state 2, state 3, because when we're in state 2, and the hardware knows that, it won't even accept state 3 packets. So we might send out pretty cool fuzz data frames, but it just gets dropped right away at the hardware, and we have no idea if the thing we send out really hits the actual software. The second thing we have that's a little bit connected to the frequency hopping that I was talking about before is response and timing constraints. Because there's a lot of traffic going on when we talk about a wireless network. We have the problem that whenever a laptop or some device sends out a request, the incoming reply has to be really quickly. So there are timestamps in each single frame, and as soon as a incoming packet comes in too late, the hardware just drops it. So again, we have the problem, did the fast packet really go up into the software, or was it dropped in the hardware? And so that's another big problem we have. And there has been attempts to really parse incoming data with a laptop in monitor mode, really look at the packet and inject reply packets, and that's just too slow, it just doesn't work. Another thing we have with wireless communication is the problem of overloads, interference, packet corruption, and so on. We have a frame checksum in management frames. As soon as there are two packets at the same time in the air, the hardware will drop the packets right away because the frame checksum is just wrong. We might have multiple wireless networks in the air. I mean, how many networks are available at your home? You know, there's probably 3 or 4. Everyone uses some unencrypted, right? So we have a big problem with packet corruption, and that's another thing. And the last thing we have on the slide there is not really an issue of wireless fuzzing, but of fuzzing altogether. We have the problem that we're really bombarding a target with packets, but we never really know when it crashes what was the last packet that really made it into the driver or into the software that we're attacking. So monitoring a target is really always a hard thing to do, especially if you don't know which packet made it into the software and which didn't. And as last thing, we have a kernel mode fuzzing right here. So how do you debug kernel mode things on a remote target and make it easy, make it fast, and so on. So we have a lot of issues that we have to deal with. So another thing we have to ask ourselves is, what do we want to fuzz? We saw before that we were mainly dealing with management frames, and that the body is made of the so-called information elements that hold the actual data inside a management frame. Those information elements are made up of the type length value pattern, and you can see it down here, maybe some of you know, but basically it's just the first byte or the first couple of bytes fixed length saying what is this information. The second couple of bytes say the length, and then there's the length bytes of value, and your security researchers, you know where the problem with all that is. You have a length field, you have data, yeah, there's gonna be some overruns and things like that. So we know, yeah, overflowing is potential, so we really take a close look at that. So here we have the example beacon frame I was talking about before. Here we see we have the header on the left top, we have a frame control, which basically says this is a management frame, it's of type beacon, and so on. We have an ID, because we need that in protocols. We have 3 addresses. One is the source, where is it coming from? One is the destination, where is it going to? And the BSSID is usually the MAC address of the router that is responsible for sending on packets, because 2 laptops might not reach each other, so they send it to the router and it will just forward it to the next router. We have the frame checksum at the end, and here we see the body. We have a timestamp that I was talking about before. That's why we have the timing difficulties and some additional information. And then we have 3 information elements. The one at the top is the SSID, which says, well, it's ID 0, it has 9 bytes, and it's just characters, just saying my network. The second one is the supported rates. So in the beacon frame, the access point saying I can talk to you on rates 11, 14, 21, and so on to 54 or maybe 100 and whatever is possible nowadays. And the last one is just ID. I think it should be, say, ID2, which says, well, I'm currently communicating in frequency 9, because you could receive a higher frequency, because you can never send it exactly at one frequency, so you know exactly where this communication is taking place. Okay, so we heard about wireless communication, we heard about the protocols, and we had heard about the problems we have when fuzzing with it. So we came up with what we call the virtual 802.11 fuzzing. And for our new approach, we took the requirements I stated before, just to sum them up once more and try to overcome these. So the first one we tried to eliminate were the timing constraints. We don't want to have to be fast to reply to a packet. This is one major requirement. The second one is this unstable wireless medium. We don't want to send out packets and them to be altered while they're sent. There might be a microwave standing right next to it and it will just be total crap, whatever the hardware is receiving. So we don't want that. The third thing is a very big point for us is we need guaranteed delivery. Whenever a fuzzer sends out a packet, we want to make sure that this one packet makes its way into the device driver. There's no need for this packet if it's dropped at the hardware, and we don't know. We might be sending hours and hours of data and it never reaches our target. So we need guaranteed delivery, and like I said before, we want additional advanced target monitoring in our new approach. And the solution was to move the target, the fuzz target, into a virtual environment, into a virtual machine. So why do we do this, and what are the advantages of doing so? Well, the first thing we have is our virtual wireless device, which is written in software. We have a virtual machine that's emulating a piece of hardware, and to be honest, this piece of hardware on our laptop is nothing else than a black box. We send something in, and we hope that something's coming out of it, but we have no idea what's going on. So since this virtual wireless device is a piece of software, we can use high-level inter-process communication to do the transmission, the injecting, and so on of our data. So basically what we do, when a fuzzer wants to inject a packet, it just tells our wireless device, please inject this using shared memory, and then afterwards uses a set of semaphores to say, okay, what did you do with the packet? Did you pass it on to the network stack, or did you drop it? And if you drop it, could you please tell me why? Was there, maybe, did you have wrong frequency? Was there no memory left in the device driver? Or was it a corrupt packet or something? So we can really query our device and find out what happened to our packet. The third we have on there is that we have a virtual CPU. There's nothing better than that. We can hold the execution of this virtual CPU at any time that we want. So when we inject the packet, we simply tell the fuzzer, oh, other way, if we see that our virtual environment wants to send out a wireless packet, we simply stop execution of the virtual machine. Then the fuzzer can go ahead, take the packet, disassemble it, look what's in there, and say, okay, I want to reply to that, that looks cool. Generate whatever is necessary, inject the reply packet, and then continue the execution of the virtual machine. So for the simulated system, there's not one single loop of execution, not even 1 microsecond between the outgoing frame and the incoming reply to the frame. So we have even less timing distance between the outgoing and the incoming frame than in real time. So we really have no timing constraints with that. And the fourth thing we have on there is guest OS monitoring. Whatever we do with casual fuzzing of wireless device drivers, we can do the same thing in a virtual machine. We can have somebody sit in front of the virtual machine and just wait for it to crash. However, we have other things we can do on a real low level. We can, for example, trigger certain events in the virtual machine. We can trigger restarts. We can tell our fuzzer, whoops, system just restarted, tell our fuzzers about it. We can hook our graphic cards, it's virtual, it's all software. So we can take a look at some pixel and see, whoa, it just turned blue. Look at the whole screen, well, everything's blue, oh, there's a blue screen of death. We can also really just simply pipe out the text that's being sent to the graphic cards and see, well, there's a print key, there's a kernel panic. That's obviously a system crash. So we can really hook system events and tell a fuzzer about it. We can go even further and install hardware breakpoints into well-known code areas. For example, we can install a hardware breakpoint into well-known code areas like the Windows blue screen of death. And before the system even crashes, we can notify our fuzzer and maybe even debug the system that's crashing. So we have a lot of additional opportunities with our new approach with a target in a virtual machine. So we have drastically simplified the complexity not only of writing fuzzers, but also of the fuzzing process itself. So our solution, like I said, it's based on a virtual machine, and our implementation is based on Fabrice Belas QEMU, which is an open source software, open source virtual machine, and just like any other hardware that you can use to be simulated inside the virtual machine, we have our virtual device as an optional Ethernet card that you can add during nice tune. That you can add during startup with command line options. And during the implementation, we also said, well, we have to stick to a very modular design. we said, well, this virtual device, we shouldn't really make it a fuzzer. We want to have something generic. So we said we have the virtual device only responsible of doing two things. The first thing is synchronize the incoming and outgoing queues of the device driver with a shared memory that other modules can connect to and inject packets and look at outgoing packets. And we also have the virtual device take care of notifying those modules that connect to the shared memory. So we can really tell them, well, go ahead and tell me about system restarts, about injected, about outgoing frames, and so on. On the next slide, I have a short picture of our system overview. On the left, you can see we have the virtual machine QEMU. We have an operating system running inside. It's either Windows, Linux, or Mac. We only tested on Windows and Linux, but there shouldn't be a big problem porting it to Mac. You have a virtual CPU inside. We have virtual memory. We might have optional Ethernet cards or just any hardware that we want. And we also have what we call 802.11 fuzzer, which is exactly an Ethernet card. It has the shared memory that outstanding modules can connect to and interact with. And down here you can see, well, it identifies itself as a Theris communication 802.11 NIC revision 1, and you will see that in a demonstration later. On the right you have modules that connect to the virtual device. We have two basic modules called dumper and listener. They do nothing else than really look at the outgoing packets and just either store them on disk or just print them out in a somewhat human readable form. Then we have the injector, which does nothing else than inject arbitrary data into the virtual device. And we have what we call stateless fuzzer module. The stateless fuzzer is basically nothing else than what was presented at Black Hat Europe this year. Stateless in this sense only means that it stays in state 1, so it does not go into authentication, association, or any encryption or any data at all. So this is very basic. However, on those two modules, or two types of modules, we have developed an access point module and a full fuzzer module that we're going to deal with on the next slides. So the access point module, it's really nothing else than what the name suggests. It's a software version of a real access point. Actually, it's simulating my Cisco router I have standing at home. It does everything a real access point has to do. It sends out beacon frames. It responds to probe requests. It responds to authentication and to association requests. And we also have a minimal implementation of the ICMP protocol inside the access point, just to make sure that higher level protocols work as well. And what turned out during the development, but also during the fuzzing process, that it's very handy to have full logging of every single frame that goes in and comes out of the virtual device. So we have full logging of the 802.11 traffic. But as words are always hard to explain something, we're going to switch to our first demonstration now. I'm starting up my tool. I'm just going to explain what I did afterwards. Whoops. I had to restart my system before. Okay, to show you what I did, I hope you can read it. I'll just make it a little bigger, this one too. Okay, up here it's a script that I started QEMU with. I invoke QEMU with a image I have on my local hard drive, and I emulate two network cards. The first one is called of type model RTL 8139. It's a basic network card, standard QEMU implementation. And the second one we added was of type WLAN fuzzer, and it's simulating an HP W400 device. You can see that on there. Make it a little bigger. Oh, still can't see, it doesn't matter. I have a virtual device set up, and I've also started the listener module over here, so it's going to show us what's going on inside the virtual machine. So I have then resumed a snapshot so I can skip the Windows boot up process, because as we saw with Jeff Moss, it might take hours. And just can continue execution, so I can switch to my virtual machine. And as you can see down here in my hardware manager, there's a RTL 8139 standard network card, and there's also an HP W400 wireless network card that I can use. Okay, there you go. So if I now take my wireless connection manager, I can scan for networks, and what I can see in my listener down out here, I can see that there are constantly frames coming out of the virtual machine. It's somewhat human readable, but on the bottom you can see that it's management frames coming out, which are probe requests. And on the top you see that the frequency is changing all the time. So that's basically just what I said at the beginning. Windows XP is sending out probe requests to find out everything it can about available networks in the area. Obviously I only started my listener module, that's why it didn't find anything. But what I can do now is just start my access point. And I'm also starting a monitor over here that will just show us a little bit about what's going on. So inside the access point I can tell it to say, I can give it some SSID I want to be announced, say, yeah, Vol 7 sounds good. Say, go ahead, start simulating the network, and in my monitor I can see, okay, it's starting to inject beacons, regular intervals. So if I turn back to my virtual machine, I can say, please rescan. And voila, you see, there's a new wireless network connection. So just to have a little fun with it, let's go ahead and connect. Say, yeah, we know it's not secure, but go ahead. You see there's something going on in the background, and you see it's getting an IP address down there, and we have a perfect connection. So just give it a few seconds to start the logging. Okay, so I can go up there where we started the logging. You can see that after injecting some beacons, we suddenly received a packet while we were not authenticated, and it turned out to be an authentication. So we simply replied to that packet, turned into state 2, authenticated, received another packet which turned out to be an association request, replied to that packet, and suddenly we were in state 3 where we can use higher level protocols. Then there were packets coming out which turned out to be not management frames but data frames carrying higher level protocols, and they turned out to be ARP requests for 192.168.3.3, which is the static IP address inside my virtual machine. So Windows XP is sending out an ARP request just to make sure that it's using a unique IP address. Afterwards there's a lot of IP traffic, which is basically nothing else than Windows trying to search for available services in the local network. We obviously don't offer them, so we simply drop those IP packets. But like I said before, to test higher level protocols, we have an ICMP implementation. So I can go ahead and say, show my ARP cache, and obviously there's nothing in there. But I can ping my access point because it's listening on the IP address 0.3.1. Just go ahead and we see we get a reply. And the background, in my logging, I see there's a data packet coming out. It turns out to be an ARP request for 0.3.1. That's me, so I reply to the ARP request. And afterwards, there's a data packet coming out, which is an IP, an ICMP packet, which I can reply as well. So we see we have full control over the network connection. We don't have timing difficulties. It's really easy to do the communication with that. And having said that, let's just switch back to the slides. So the next module I want to talk about is the stateful fuzzer module. Unlike other fuzzers that has been published, we do stateful fuzzing, so we go into state 2, we go into state 3, and do everything we can there. And the fuzzer module really behaves like the access point module, but we can tell it to replace single packets with a fast version of it. So we can really say, fuzzer module, go ahead, act like an access point, and as soon as we receive an authentication, we want to reply with a fast packet. So we can really pick out single packets and fuzz these. And we will also show this module in a second. But I'll just sum up the results of the fuzzing we did. I showed you we developed a framework for fuzzing wireless device drivers using the virtual machine QEMU. However, we can not only use it for fuzzing, we can use it for just about anything. We can use it to test new wireless protocols. We can use it to test new device drivers. We can do anything we want to it, or we can just be cool and have a wireless connection on our virtual machine. And we have, with a simple fuzzer, we have not only stateless, but also stateful fuzzing in all 3 states of the communication handshake in management mode, but it can be extended to ad hoc mode and so on of wireless communication. It's not a problem. And to see if our fuzzer really works, we have taken an old version of the Mad Wi-Fi driver for Linux, have run our fuzzer through it and found just about any bug that was previously published. However, the good thing about it was by switching to a new version of Mad Wi-Fi, we also found a previously undocumented vulnerability. And how easy it is to find this vulnerability using our framework. I'm just going to start the second. Oops. Resuming and the snapshot again. Yeah, it's an old machine. Okay, so we're inside a Kubuntu version, Kubuntu Linux, fairly recent kernel, and I've written a script for scanning. So this script does nothing else than activate our wireless network, and then, so I can really hardly, but it says IW list Atheris 0 scan, so it's just constantly scanning. And like I said before, we're simulating an Atheris device, so I can use LSPCI, and I can see down here that we have a network connection, network card Atheris communication AR5212, just like I said before. So if I start my scanning now, I can see again, well, there are frames coming out to search for wireless networks, but this time I'm invoking my fuzzer, and I can tell my fuzzer what do I want to fuzz. I can tell him, well, I can either fuzz beacon frames, I can fuzz probe responses, and so on. I can tell it how do I want to fuzz it. I can say, for instance, I want to fuzz probe responses. I can tell it how do I want to fuzz the packets. Do I want just plain overflowing, or do I want to inject string format vulnerabilities? Just use overflows for now. And I can tell it, like I said before, I can tell it which packet do I want to fuzz. So I can wait for a certain event. I can simply use regular time interval, but I can also wait for a probe response, probe request to come in. And I can also tell it how often do I want to inject a packet. And since I know that the vulnerability is in information element 48, information element 50, I'm just going to start with number 48 and just invoke the fuzzer. You can see there's scanning going back there, and I see, okay, we fuzzed information element number 48, nothing happened. I inject beacon, so right now I'm waiting for a probe request to come in, and as soon as I get one, I fuzz my information element number 50, and you can see in the background, well, kernel panic, and it's even telling me where the problem is. So you see how easy it is to do stateful fuzzing, and also you can see that my fuzzer didn't continue fuzzing because it knows, okay, something went wrong. So with that, we can see, whoops, that was wrong. That was wrong. So we can see that we found a vulnerability in the last Mad Wi-Fi implementation. It was a frame that we send in about extended supported rates, and it totally crashes Linux systems. There's no remote code execution possible, but it's really easy to send out denial of service packs. So as soon as you will receive one, your system totally crashes. And together with Second Salt and our secure system lab, we have published the vulnerability, and it's been fixed in the latest release of Mad Wi-Fi. Okay, so now to continue how we might use this vulnerability, I'm just going to hand out over to Sylvester. He's going to talk a little bit about kernel mode exploits.
Okay, I hope this works. So we listened to Jeff's keynote this morning, and we thought, how could we make our presentation a little bit more like a Darth Vader presentation? So we thought, well, we could, put in more and more content. So now I'm going to talk about kernel mode exploits. You just saw the kernel panic, and before we started fuzzing, of course, we asked ourselves, what kind of vulnerabilities could we find in kernel space, and if we found them, could we exploit them, and how could they be exploited? And also, or especially since we're fuzzing wireless devices, could we exploit them from a remote machine? And also, we asked ourselves, how generic could these exploits be? Could we, just come up with an exploit and put it into Metasploit, for example, so that if our fuzzer finds a vulnerability, we would be able to, adapt a few parameters and have a working exploit. So that would be really nice. So what we did, we started, reading lots of FRAC papers on kernel mode exploits, and we focused on Linux because we like Linux, and we also had initially only wanted to fuzz the Mad Wi-Fi driver. And the first thing that we found that I'm introducing here is a very simple, or very simple in theory. We included it because it has a few important concepts, and it's the so-called null pointer or user space pointer dereference vulnerability. And that's basically you have a pointer in kernel space, or a stray pointer in kernel space that points into user space. So if that pointer is dereferenced, then something unpredictable is going to happen. But now if you have a local control over the process in context, or over a user space process, you could simply mmap the area that the stray pointer is pointing at, and you could create all kinds of interesting exploit scenarios from there. So if you have a direct, or what's called a direct dereference, if it happens in the context of instruction execution, that would be a very trivial case to exploit. But there are also more interesting scenarios. For example, if you have here in the first line a call to kmalloc. Now, if that call to kmalloc fails for some reason, if there's not enough memory, or if you are in control of the size variable in some way and you can just make it insanely large number, and the kmalloc fails and is not checked, you might have a null pointer in the variable foo. And now, if sometime later, something is written to that, or to a structure that is expected to be where foo points to. Now, foo is a null pointer, so it points to address 0. But address 0 is, of course, in the user space. And we just tried this out a couple days ago in the lab. It's quite funny. You can just, on Linux, map the 0 page in a user space process. And so you could just mimic the structure that's expected to be there. And of course, if you have control over, in this case, the data pointer, you could let it point anywhere you want it, and you would have a controlled write. And of course, there are many exploitable scenarios that can derive from this. So the next class of vulnerabilities that we looked at, or the problem with this class, of course, is that you need a local process. And for us, if we think about fuzz or exploiting wireless devices, we don't have that. So we looked at something else, heap overflows. We had this talk yesterday about heap overflows. In the kernel, you have the kernel memory allocator, which is normally the slab allocator. And you can set up so-called look-aside caches with memory objects that all have the same size. And when Linux starts, it actually creates pools of such caches with very small objects. And if you make a call to kmalloc, for example, it will simply pick one of these objects for you. So what is a slab overflow? A slab overflow is simply if you write beyond the boundary of one such object and into the adjacent object. So it's something like this. And again, you could try to exploit the metadata, but also the data, as we heard yesterday, that is in the next slab. But for this to work, you need to know, what kind of memory object is there that you're writing into, and then you could maybe exploit by overwriting a function pointer in that memory object. Okay, I just started and already get the red card. Again, that's something. I mean, these exploits work by forcing the kernel to create certain objects that you know can be exploited. But again, you need a local process to do this. And so we looked at stack overflows. Now, stack overflows, the kernel stack is different from the user space stack. It's only 8K or maybe even 4K. And you have, it starts at the top and grows towards the bottom. And at the bottom, we have the thread info structure, which points at the process descriptor. And I mean, in theory, the stack overflow exploit works the same for kernel stacks as for user space stacks. You place your shellcode in a buffer, and you want to override the return address. So, but that's the first problem. How do I know where my buffer is? So you can use the chump ESP trick. That if you know a chump ESP instruction somewhere in the kernel memory, you could, point to that, and after the return instruction, the stack pointer will be placed to the memory object right above your chump ESP address. And so there, because that's basically in your overflow, you could point back to the beginning of your buffer. You wouldn't even need the knobs in this case. But that's already the start of the guessing game. You need to know where is the chump ESP in your kernel. And also you need to know where's the return address that you're overwriting, because we had it up here, but it could be down there also. And what if I don't know it? You could do a similar trick, and that is insert the address of return instructions in the kernel space. Then you would just basically after the first return, the ESP would point or the return would pop off one value from the stack, and you would return again and again and again until you hit your chump back to the beginning of the buffer. So that way you could, if you knew the chump ESP address, you could hijack control flow in the kernel. But that's only the start. We're here either dealing with a system call, so we're in the context of a process, but we might also be in interrupt context. In fact, if we talk about wireless devices, we're probably in an interrupt context, because a packet will arrive and the interrupt will be triggered. Probably it will set up a tasklet, so to defer execution, and we will run later in a soft IRQ context. But again, we will not have a user mode process in our context. And the thing is that kernel mode exploits sound very cool, but at the same time, you'd like to get back to user space, because you can use all kinds of libraries, and it's harder to really mess up there. So you would like to come back, but if you're in a interrupt context, you don't even have a user space process, or you don't know which process, and it could be a critical process that you cannot really hijack. So what you'd like to do is you want to set up your exploit or place it somewhere else where it's safe, and install a hook for later on. And then you would have a user space process later on triggering your hook that would then execute your second payload or copy it to the user space process and execute it there. So if you take this concept, you would like to have exploits that look something like this. You have the kernel mode exploit wrapped around a normal user space exploit that you can send to the target, and ultimately it will execute your user mode exploit with root privileges. And that's exactly the way Metasploit tries to handle Windows kernel mode exploits. And it does this by dividing the exploit into these sections. We have migration, staging, recovery, and the stage. And this is basically what we saw on the previous slide. Migration, you need migration if you, for example, are in an interrupt context. The stager basically copies your payload to a safe location for later on. And recovery is something that's very important too, because if you're a stager, you have set everything up for later, but now your vital kernel thread crashes and the whole system goes down, and your payload, everything will be for nothing because you could have crashed the system to begin with anyway. So recovery is vital for these kinds of exploits. And you have the stage phase, which ideally would be only a user space payload. So since we're running out of time, I think only a few words on the stager phase, because that's one of the most important phases. There are two questions that you need to ask yourselves. Namely, where can I copy my ring 0 or ring 3 payload? I need a ring, or if I have a ring 0 payload, then I basically need a two-stage stager, or I need two levels of a stager. And the second question is, how can I install a hook that later on will execute my payload in a context that's desirable for me? So to really make it short, we copied our payload to the interrupt descriptor table because there are many empty entries there. And we installed a system call hook. We hooked the sys execve function. Okay, so to come to a very brief conclusion, 802.11 fuzzing is very cumbersome for the reasons that Clemens told you. By moving the target into the virtual environment, a lot of things get easier. The downside is that you have to implement the virtual device. But we believe that for manufacturers, for example, who have all the specifications of their hardware, this would be easy. And then, as I hope to have shown you, that kernel vulnerabilities are not too different from user space vulnerabilities, but to exploit them is more complex simply because you have to, because of the complexity of the kernel itself, and it's easier to mess up in there. And it might be able, or it is possible to write generic exploits, but you still have a number of parameters that are really important. For example, the address of the jump ESP, it gets more complicated with the recovery, and in all the cases, you need to know really in what kind of situation does my exploit occur. Really every vulnerability is a story of its own. Here we have put in a few references, QEMU that we used in the demo, and a paper in the most recent FRAC edition, which gives you a good overview over kernel exploits. And if you check the references, it also has many interesting references. And finally, we'd like to take this opportunity to thank our teachers, Chris and Engin. Engin is right here at the back, who are really cool teachers, and our advisor at SecConsult, Bernhard, who owns the web hacking server out there and is also really good at the Wii bowling, I'm told. So he really helps us a lot too. And so now we have hopefully a few minutes before lunch to answer a few questions, if you have any.
Everyone hungry?
Just one question. What we don't catch in these cases when you're doing this virtualization is cases where you have problems in the firmware of the driver. We already have seen problems like that. I think that's a major class of problems you can't catch with this approach.
No, that's that's true. Yeah, actually, we introduced new problems like that because we have to reverse engineer the firmware and then deal with it. But like I said before, we have those 2 layers, the physical and the Mac layer, and we only concentrate on the Mac layer because that's what we can exploit on a broad variety of drivers, maybe. But yeah, you're right. We don't get.
So, but that's also, you know, we're just dealing with the software driver anyway. So.
Another question. Many drivers have firmware. For example, the Atheros driver, the MacWifey driver, has parts of the firmware not as a firmware image, like most drivers have, but as a closed source.
Yeah, but not much longer though. No, they just made the announcement in September, end of September, that they're changing over to the OpenHAL version. There were some allegations that the OpenHAL version used illegal parts, you know, from Atheros, but basically they had investigations, and it came to nothing. So now they decided, you know, to go all open source.
But still, that doesn't really, that's not really a problem for us, because even if there's a problem inside its binary-only version, we already find that. Yeah, exactly. It crashes, and we know, and we can do some reverse engineering on the binary.
You have to know exactly what the driver does.
Well, we're fuzzing Windows drivers, and we have no idea of the source code there. So we're fuzzing everything.
Yes,
so
but this means you have to have some knowledge of the hardware.
Well, you need to do reverse engineering basically, but that's the why we believe it would be more easier for the vendors themselves.
Yeah, but actually, you know what I started doing when I walk around in this room? I see, oh, there's a laptop from somewhere, and I know that's an Atheros card right here. Just because I've started looking at laptops and I see, okay, well, I see somebody there with an HP laptop, it's Linux, so I gotta start my choose.
I hope it's a patched version.
No, really. If any laptops crash this afternoon, I'm sorry.
We did. I mean, you know, the virtual fuzzing. Of course, we tested it, you know, in real life.
And it's so easy to start programming. Yeah. So that's the funny part about it.
So you verified with real hardware before.
Exactly. Yeah. We didn't
Yes.
find any false positives that crashed on the virtual machine, but not in real life. But we tried everything, whatever we found.
I mean, if we, you know, find or if the system crashes, it might be because something in the virtual device is wrong, of course. So you need to verify with the real hardware.
But it's a matter of minutes, seconds. Any other questions? Yeah?
What, you said that you didn't find any false positives.
Yeah.
Did you find any false negatives?
Well,
you probably know, of course, but I mean, there are situations where, because you control the timing so efficiently on your virtual machine, where in reality you can't really exploit it because you can't get the timing that right, or well, you could, but the chance of that happening.
well, when we do stateful fuzzing, there's always a problem with timing, things like that. But we didn't find anything like that. And to be honest, what we really try to present here is not the fuzzer itself, but the framework that is really beneath the fuzzer. And the fuzzer that I wrote was about 3 hours of programming, really hacking together some parts of Wireshark and my framework, or our framework. And it was writing exploits, exploits or fuzzer, whatever, using the framework is really straightforward. So the really big part about it is the framework itself.
So
I asked because you do simulation and visualization and things, and I've noticed like if you're debugging in an exploit, just by actually you do it like step by step, it ends up happening completely different from when it happens in real life. So you actually might work flawlessly in a debugger, so if you run without a debugger, it doesn't work.
Yeah, obviously.
So if you encounter that,
No, but I think the best thing right there would be just to find vulnerability and then switch to real hardware and go on exploiting it right there.
But also because you're not trying to find the exploit in the first step anyway, but just the vulnerability. I mean, if you find something and you investigate and then you find out that you can't reproduce it, it's still.
Anything else? Other Thank you for your attention.